Good morning. Today we're going to continue working on the initial value problems. Remember last time we did the Euler method. So we use one equation and one example, and we compare the exact solution, the integral of that equation. And compare it to the Euler equation, and we found out, if you remember, if we go back and let me share my screen here to the code here. Let me open MATLAB, and let me just do this. We talked about that if you really decrease the value, for example, if you start at 0.01, and then you run this, you're gonna be a little bit off. But again, if you decrease the value of the increment h, you're probably gonna get better results. See here, you're getting close to the exact solution. Look at the difference. And if you again go smaller and smaller, you will actually get very close to this, your 3.87 and 3.89. So that is Euler equation. Today we're going to do the Heun equation, Heun method, and I'm going to do the RK2 method and RK4, which is the most popular one. We're going to use the same example, which is the dy dt will be dy dx is equal to x times y. This is the equation that we used right there. So we're going to use the same thing, but we're going to use different method. And you know what? Let's copy whatever we did in here, and we're just going to change a little bit of this program, because we're going to do the same thing. We're going to just change a little bit the slope in there. So let's just put a new one here, and let's paste this, because we're going to do some minor modification. So a couple of things that you want to do in here. So it is, you can just do, we're going to do the same for loop. We're not changing anything in here. So let's modify a little bit that. Remember the Heun, let me just call this Heun now. The Heun will take the Heun here. The Heun method will take, remember, the slope at yi or at xi, and then it will take the slope at xi plus h, and then it takes the average of that. So you sum both and you divide it by 2. Instead of having the slope, remember here we're just taking the slope at t, or at, in this case, x equal xi. So if we go back, let me just show you exactly what I'm talking about. So we'll go back in here just to show you. So if you see here in the Euler equation, if you look, we're just taking the slope at this one. That is what we have, the increment function or the slope. Now in a Heun, so the Heun, we are taking the slope at this point and slope at the end of that increment, which is, again, in this case, ti plus h, and then we take the average of that and multiply it by h. Okay, so that's exactly what I want to do. So let's just modify a little bit of this, and if you notice here, so we're going to change some things in here. So again, y in this case, we're going to do k1. Let me call k1 because I'm going to use that later on as well. So k1, I'm going to call this is dy of x and y, right? That's the slope. That's the slope of that one. So we're not changing that one. I'm get used to K1 and K2 and K3, because once we start doing RK2 and RK4, we'll be able to use K1, K2, K3, K4, and then do the RK4 equation. So let's do y nu here. I'm just going to simplify it here. Is equal to y plus dy, right? Or dy xy, or you can just do k1. Let's just do k1 here. K1 times h, right? Times h. And what do we mean by that? Because we want to get y nu. Y, the first y that we have is at x equal xi, right? Now we want at xi plus h. That's why we multiply k1 times h. And in this case, y will be equal to dxy times h. Well, let's hold on this. We're going to do x nu first. So x nu will be equal to x plus h, right? So now we're getting the property x u and y nu at the end of that increment. And now we want to get k, in this case, k2. K2 will be equal to the slope at x plus h will be equal to dy, right? X nu and y nu. Okay, so and let's do that. So, you know, if you really want to simplify it, you don't want to put x nu and y nu, you can just do that. You can just take this, copy, and do that here, right? And you can take this one here, copy, and do this one here. Paste it in here, and then get rid of these two. I try to simplify it, but you can do whatever you want. So that is K2, K1, and this is K2. Okay. Now, y in this case would be equal to, let's do y would be equal to K1 plus K2, and times here. Let's just put the here and here, and that's 0.5, half. We're taking the average of K1 and K2. Okay, and that's it. So x, we really don't need this one here. Well, you can just keep this one. Yeah, you can just keep this one. That's fine. Let's make sure that what we did is right. So we're taking the slope at xi and the slope at xi plus h, and we're taking here the half of that, and then we'll, okay, that should work. But let's save this as Heun. Just save it, and let's run this. So if you look here, very close, huh? Very nice. So let's see if we decrease the increment h. I'm going from 0.001. You see, it's still getting good. If we do this 0.01, let's see here. Yeah, it's not bad. And if you do 0.1 and hit that, you see it's still very close. So even with the small increment, the Heun equation is a bit better than the Euler equation. because if you see that really it works even at small at actually large increment. So, and if you just do 0.01, you'll see that you're just very close to the exact solution. Okay, so this is Heun method. Again, Heun method, we're taking the slope at the starting point, which is xi, and the slope at xi plus h, which is that increment, and we average that and multiply it by h, and that's how we're going to do that, how that we are integrating this. Okay, so that is great. You know, since we already did this problem and we write our own codes in this, again, it's the same code that I read. I just changed a little bit in the 4 because we have now K1 and K2. Now, we can actually use it to solve some of the in-class problems or homework problem if we decide to. So that is Heun equation method. So let's see what the RK2 method will give us, because the RK2 method will also give us a good, more accurate than the Euler method. So let's see what we get in there. All right, so this is the Heun method. Let's, you know what? Let's do that. Let's copy this one here, because we're not changing a lot of things, only in the for loop, and let's start a new one. And let's paste. Now, the RK2 method, instead of taking the slopes of the starting point and the ending point of the increment, we're taking the slope at the midpoint between xi and xi plus h. Okay, so and let's see how this will fare comparing to the other one. So right, so this is we're going to have only actually so this is K1 is not changing, so that is to K2, and K2 in this case it's going to be x nu, and x nu in this case will be xh over 2, right? That is over 2 because it's half in the midpoint, and y will be equal to y plus K1 times h over 2 in here. So that is over 2. Okay, nothing, we're not changing anything. We're getting the slope to the midpoint. That's why we have h over 2 in there. So that would be, again, x plus h over 2, and y will be plus K1 h over 2. Now, here we don't have to, we just have to multiply by K2 here. So let's get rid of the 0.5. We're not taking any average. We're just doing this at the midpoint. So yeah, K2 here. All right, so it's y plus K2, x plus kx. Okay, so K1, again, it's the slope, and K2, we're taking the slope at the midpoint, and that will be y2. Y will be equal y plus K2 times h, and then x will be equal x plus h. Yeah, x will be equal to x plus h over 2. So yeah, so let's just do over 2 here. Well, let's just K2 times h and x plus, let's just leave it h here, sorry. Okay, and let's save this one here. save as, and I'm gonna just call this RK2 or midpoint, whatever you want to do, RK2, and just save that. Let's see what we get. Let's do this. Wow, this is good, even with 0.01. Let's just do 0.1. So 0.1, I'm just comparing these numbers. So even with 0.1, you're still 7.31 to 7.389. So if you just increase it a little bit, decrease it a little bit, H, look at this, 3.88, 3.89. Also very good. It's very good comparing to Euler, okay? So far we did Euler, we did the Heun, and we're doing the RK2, and finally we're gonna do the RK4 before we start doing more problems using these. So if we do the RK4, so if we're gonna do the RK4, let's keep, let me copy all of this and open a new one. And again, we're doing the same equation, so it doesn't really matter. So let's, let me open back the RK2 because I want to change this to RK2 here also. So RK2, and just save it. Remember we did Euler, this is the RK2, and we're doing this one here, and that's going to be the RK4. Okay. So changing in the for loop, that's all I want to do. So in the RK4, we want to actually do the, we're going to do the same thing. It's not going to matter that much. We're just going to introduce K1 and K2, K3, and K4. So let's see what we get in here. So we're just going to actually modify that loop. So we'll see here. This is K1. K1 is not changing. Let's do K2. So K2, K2 will be, if I go back to the RK4 equation. So here we go. Okay, so that is the RK4 equation. This is K1, if you see, and K2, K1 is not changing, so we're going to change K2. We're going to introduce K3 and K4, and then we'll do this equation right here. Okay, so yeah, let me do this here. All right, so again, we're just modifying that loop. So K2 in this case will be equal, it's going to stay x plus h over 2. So we're not changing that. And y plus 1/2 K1 over 2. So that is also good. Okay, we're not changing that one. So let's do K3 here. K3 is equal to also dy, and in this case also same thing, x plus 0.5 times h, same as we did in K2, but y in this case will be equal to 0.5 times K2 times h. Okay, so that is yeah, x plus 0.5 h. I'm just doing this equation K3, and now K4. Oh, I forgot y I here, y plus. So don't forget that, y plus, and this is x plus. Okay, very good. And now we're doing K4 here is equal dy, and this time x plus h. If you look here, it's x plus h, and here is y plus k3 times h. So x plus h and y plus k3 times h. Okay, so that is k4. Now y, I'm going to change this because y is equal to 1 . Yeah, let's just do this one here. Just make sure I didn't make any mistakes. So y is equal to 1 x plus 1 over 6 times k1 plus 2k2 plus 2k3. Okay, remember the weighted values for k2, k3 is double than k1 and k4, and that's why you get more accuracy, plus k4, and then this times h. Okay, and let us suppress that. X will be equal x plus h. So that's it. So let's see what we get in here. Again, we're doing the RK4, and let's do the 0.01. Let's save this as the RK4, and just save it. And let's run it. So if you see here with 0.01, you see the accuracy with the RK4 is unbelievable. I mean, if you just do 0.1 and you hit, you'll see 7.388, 7.389, even with the small increment or large increment of h. Remember when we did 0.1 with the Euler method, it came out like there's our value was 5 point something, while the exact value was 7.38. So I'm just comparing this, so you'll see the accuracy of the RK4. I mean, even with 0.1, you will see that it's very accurate. If you go 0.001, for example, you'll see that you're going to see it is pretty much the same. Look at this. Look at the accuracy comparing to the exact solution. So that is pretty much it. Compared to the Euler. So what we're going to do, we're going to do now a couple of problems using those codes that we did. So let me pull the let me pull those E-class problems. So this is the problem that we want to do. Let's read this problem here. It says solve the following initial value problem over the interval of t equals 0 to 2, where y of 0 is equal to 1. So it's given us the initial condition of it. Display all the results on the same graph. And so there's, we can do this in 4 ways. So first, we're going to do this analytically. So do the integration, and then we'll do the Euler method with h equal 0.5 and 0.25, and we're going to do the midpoint method with h equal 0.5, and also the fourth order method with h equal 0.5. the things that we want to do in there, and we're going to try to plot all of them as well to see if see how we're going to do that. So yeah, let's see what we can do in here. You know, let's solve this one first. So here is the first order differential equation. So we want to plot these and see the equations for that. So how do you solve something like that? Let's just do this one here. So just do the integration here on both sides. So if you do this, this is going to be dy, the integration of dy dt. All right. I give you natural log of y, and if you do the integration of, I mean, what I did is just separate the variable. Let's do this here. All right. Let me delete all of these. Not this. All right. Okay. So let's separate the variable first, and then so I'm going to bring the y in here and the t in the other side. So I'll factor y out. So this is y, t squared minus 1.1, and I'll separate the variable. So dy over y is equal to t squared minus 1.1 dt. So now you can do this. So if you do this, this is natural log of y, and this one will give you t cubed power 3 over 3 minus 1.1 t. Okay, plus c. If again the initial conditions, we said that at t equals 0, what that will give us. So at t equals 0, y of 0 is equal to 1. Is equal to 1. So let's do that here. So if you at t equals 0, it's going to give you natural log of 1, right? Is equal to, this is 0, 0 is equal to c, which is going to give you, in this, the natural log of 1 will be equal to 0. So c equals 0. So if you do this, you can solve for y. Y will be equal e to the power t to the power 3 over 3 minus 1.1. That is the exact solution. So we're going to plot that, and we're going to do the Euler, and we're going to plot all of them and see how they fare. All right. So let's do that. We're going to go back to that equation that we did, and all right. So we solved this by hand, and we want to do Euler, midpoint, and fourth order RK method, and verify that that these methods will work when it's compared to the original or the exact solution. All right, we'll stop here today. Next time we'll write the code for these 4 methods, and we'll compare them all. So I'll see you in the next lecture. Thank you very much.